Two masses m1 and m2 are initially at rest, with spring compressed between them. What is the ratio of the magnitude of their velocities after the spring has been released? So there are two masses which are connected by a string, and then someone has compressed the spring by pushing two masses from both ways into the spring, and then a spring is compressed, and now they are at rest because there is no more push. So as usual, let's imagine the problem. So here I have schematic diagram to understand the question very well. So these two masses are connected by a spring, and just imagine that someone has pushed these masses from both sides into the spring and then stopped. So now they are at rest. So the only force is the force which is stopping them to go away from the spring, because we know that if I or someone has pushed the masses into the spring, a spring must have compressed, and now a spring is in compression, so all the energy is stored into the elasticity of the spring. So as long as I am applying the force both ways, the masses will remain at their position. So the velocity of mass m is 0, and similarly velocity of mass 2 is 0 because they are at rest. So my force is only stopping them to go away from the spring, because we know spring is pushing them out in opposite direction to my force. So I am just applying this force to keep them at their positions. So their velocities are 0. So when I will remove this force, they will immediately go away from the spring. Spring will expand, and they will start moving away from each other, two masses. So we call the velocity of mass m after my force is removed as Vf1, and velocity of mass 2 after my force is removed is Vf2, and we can see that these two velocities are opposite in direction. So actually I should write them as Vf1. If we say that if a vector which is directed towards the right is positive, then a vector directed towards the left should be negative. So I can write it as negative Vf2, because velocity is a vector quantity, and for vectors we have to take care of the direction. So here I have an animation. It may not look very natural, but I hope it will make you understand the motion. So here is the spring which is compressed between two masses m1 and m2. So just imagine that there are two forces from right and left which is pushing the masses towards the spring. So spring is now compressed. At this time, Vi1 is the velocity of mass m1, Vi2 is the velocity of mass m2, and of course these two velocities are 0 at this time because they are at rest. So now just imagine that I will remove forces from right and left which is stopping them to go away right now. So I am removing those forces, and let's see what will happen to the motion. So the motion will go like this. The spring will expand, masses will go away from each other, and they will arrive at certain maximum displacement, and then they will come towards each other. And then once again the spring will be compressed, and because of the compression it will expand, and because of the expansion it will compress. So a motion like this will go on indefinitely. It will never stop in our situation because we are ignoring frictional forces, and the spring is ideal. There is no dissipation of energy, so a motion will remain like that. And the final velocities, you can see Vf1 is the final velocity of mass m1, vf2 is the final velocity of mass m2, and then we will calculate the ratio of these two velocities. So now we can go to calculate the ratio of the magnitude of their velocities, and of course the ratio is actually involves the final velocities of the masses, because we already know the value of initial velocities, they are 0, and we are given only masses and velocities. So how can we calculate the ratio of these two velocities? Is there any quantity which involves only mass and velocity? Just think about it. Maybe you know a quantity which involves only mass and velocity. Mass multiplied by velocity. Is there any quantity like that? Yes, I think this quantity seems very familiar. Mass multiplied by velocity. Yes, you are right. This is momentum. This is momentum of the system. So this is a complete system and mass into, so maybe momentum can help us. So at the first stage, a system was in this form, in compressed form. This whole system, spring and masses together. And then an event occurred. That event was I removed the forces which were working from the right and left sides. And these two forces were preventing the masses to move freely. And then this event occurred. The event was removing the right and left forces. And as soon as the forces were left, the system started moving. So it was moving right and left. The masses were moving right and left, like I showed you in the animation. So momentum. How can we use momentum to calculate the ratios? Yes, there is a law. It is called law of conservation of momentum. And it says that total momentum of a system should be equal before and after an event. And then this event can be anything. In our case, this event is the removal of the forces from the right and left sides, because these forces were stopping the masses to move freely. So the event occurred as a result of the removal of these external forces. So we can use the law of conservation of momentum in this case, that the total momentum when these forces were acting should be equal to the momentum of the system when these forces were removed and system was free to move. So let's do it here. So I can write it that momentum before the event equals momentum after the event. And now you know what is this event. It is removal of the external forces. So we know momentum is mv. So I can write it like the momentum before event, it was m1 and vi1, velocity of mass m, and I is telling us that this is the initial velocity or the velocity before the event, plus because the second mass is also part of the system, so we have to put its momentum too. So vi2, and this momentum should be equal to the momentum after the event. So after the event m1, and the velocity of m1 is vf1 and vf1, and just remember that we imagined that if velocity is directed towards the right, we will take it positive, and if velocity is directed towards left, we will take it negative, because they are in opposite direction and we have to mention it in the equation. So I will write vf2 as negative, because this is directed opposite, exact opposite to from vf1. So when I am writing the momentum of mass m2, I will write negative minus m2 and vf2, final velocity of mass m2. So here we have the equation, and we know that vi2 or vi1, they were 0 before the event. They were just still at their positions. So this left side will become 0. So I will write the expression on the right side. So m1 vf1 minus m2 vf2 equals 0. I have just reversed the sides. So let me take this expression to the right side. So I will add this expression at both sides of this equation. So I will get m1 vf1 equals m2 vf2. Because I want to calculate the ratio of the velocities, so I will divide both sides with vf2, and I will also divide with m1 vf2, and I will also divide with m1 because I don't want m on this side, because I only want to calculate the ratio of the velocity, so I want to get rid of m1. So I will divide both sides with m1 as well. So we know that these two will cancel out, and here vf2 will cancel out, and let's rewrite this expression clearly. vf1 divided by vf2 equals m2 over m1. So we have found the ratio of the velocities, and we see that it's equal to m2 over m1. Here is the answer to your question.